Group 18 elements. In group 18, first element is helium, second is neon, third argon, fourth krypton, fifth xenon, and bottommost sixth is radon, which is a radioactive element. Finally, decay to stable lead isotope. Group 18 elements are also known as noble gas. Group 18 consists of 6 elements that we already discussed, and their general electron configuration is ns2 np6. Helium do not have p orbital, rest of the elements having a completely filled p orbital. Now, in our atmosphere, noble gases constitute roughly 1%, and out of which argon is the major constituent. Most abundant among the noble gases is argon in our atmosphere, and commercial source for it. All the noble gases are monatomic, and the only type of interatomic interaction in these elements is weak dispersion force, and that is the reason noble gases have such a low melting and boiling points. These are atoms of helium. They do not interact with each other, keep on passing from one point to other, but do not interact to come close. And that's the reason helium having such a low boiling point, 4.2 Kelvin, very close to absolute zero. And it is among the coldest substances known in the universe. And here we see at such a low temperatures what happens when their kinetic energy is significantly small. There exists a dispersion force, meaning the electrons, clouds, distortions will start interacting with each other, and that is the reason of their condensation at low temperature. But for going for heavier elements, these condensation temperatures are fairly high. The temperatures at which they come to liquid state are fairly comparatively high for neon, argon, and krypton, as atomic mass will keep on increasing. Let's look at the table first. Here you see, as we go up with atomic mass or atomic number, melting and boiling point both will keep on rising. Consistently they keep on rising. The reason is because this dispersion forces increases with increase in size, and these interactions are stronger. Now, atomic radii. Atomic radii increases down the group with increase in atomic number. Same point we discussed is responsible for increase in melting and boiling point. Atomic radii increases down the group. Next property, ionization enthalpy. We know noble gases having a stable electron configuration, so it is not that easy to remove electron from such a stable electron configuration. But down the group, as size increases, distance of the outermost electrons from the nuclei increases, and force of attraction reduces. That is the reason as you go down a group, ionization enthalpy reduces. We saw a reduction in ionization enthalpy from 2372 kilojoule per mole for helium to only 1037 for radon, fairly small. Next, electron gain enthalpy again. Because they have a stable electron configuration, they are not interested in taking more electrons from outside. That is the reason they got a high electron gain enthalpy, positive electron gain enthalpy. Looking at the chemical properties, noble gases know because of this stable electron configuration, they are least reactive, and their inertness to chemical activity is attributed by, we know, by the completely filled electron configuration. But still, certain chemistry we know in form of xenon fluorides, where xenon reacts with fluorine in excess of xenon. That's the reaction at room pressure, 100 pascal pressure, and at a temperature of 400 degrees Celsius, 673 Kelvin. When xenon reacts with the pure fluorine, which is highly reactive gas, we are getting a xenon difluoride. Next, xenon tetrafluoride. We are obtaining these by same fluorine reacts with xenon in ratio of 1 to 5 under a high pressure and temperature conditions. Here temperature is further 600 degrees Celsius and 7 bar. We are getting xenon tetrafluoride. Xenon tetrafluoride we get. Next reaction, xenon hexafluoride. Here what happens? Again, same, we are preparing it by reacting with fluorine, but here ratios are fairly acute. Xenon to fluorine ratio is 1 to 20, and conditions are very high pressure, 60 to 70 bar at roughly, temperature is roughly 300 degrees Celsius. We are getting xenon hexafluoride, which having a distorted hexagonal structure. You see here, this is a like hepta position, 7 positions. One position is occupied by lone pair. Now, there is another way to prepare xenon hexafluoride. That is by interaction of a xenon tetrafluoride with, like O2F2 at a 143 Kelvin. We are getting hexafluoride compounds of xenon with the liberation of oxygen. Same structure. But remember, one position, it's not a pure octahedral geometry. One position is occupied by the lone pair. That's why it has a distorted shape. Hydrolysis of xenon tetrafluoride and hexafluoride with water gives us, Xenon Trioxide, and it got a pyramidal shape because one lone pair occupies this one position, prepared by the hydrolysis of xenon tetrafluoride with water. And remember, what is the output product? One is a xenon, one is a xenon trioxide, HF, and oxygen. In this reaction, oxygen comes out, and here when ratio of the xenon tetrafluoride to water is 1 to 2 in molar terms. Next reaction is xenon hexafluoride. When water reacts with here 1 to 3 molar quantities, we are getting xenon tetra oxide, so xenon trioxide, and 6 HF molecules. Xenon trioxide is a colorless and explosive solid. Further, partial hydrolysis of xenon hexafluoride gives us oxyfluoride, which is xenon oxytetrafluoride and xenon difluoride. The shape is close to hexagonal, in which equatorial positions are occupied by 4 fluoro groups, and one axial position is occupied by oxygen, another is by lone pair. Again, this is a partial hydrolysis. This is a hydrolysis of xenon hexafluoride. And control quantity of reactions, here we put a 1 to 2 molar quantities of xenon hexafluoride in water. We are getting xenon dioxide with xenon difluoride compound. Applications. Now, among the applications of noble gases, one is achieving the cryogenic temperatures. Noble gases are used because they are used like in enamel machines to provide a highly cold jacket, cryogenic jacket for the supermagnets, superconducting materials, because superconductors provide such a strong magnetic fields only under certain cryogenic conditions that are achieved using these liquid form of noble gases like helium. First is, it's also used because helium, we know, is not flammable, so it's used in meteorological balloons, where we'll use big balloons filled with non-flammable helium, because hydrogen, although lighter than helium, but it can explode. So we use helium. It's a stable and safe gas. And at the bottom, we connect all our equipments that are required to monitor different atmospheric layers. Second is, helium is a very good conductor. So to use as a heat conducting material, it is used as a coolant in gas-cooled nuclear reactors. Here you see, it's a nuclear reactor. Although the model is not accurate, but it is giving you an impression how it happens. Here is a nuclear reactor. Here what happens, in this coolant loop, in gas-cooled reactors, we will pass helium gas. Helium will take away the heat from reactor and transfer here, where it is used to convert this water into steam and for generation of electricity. So this is a simple example, although it will not give you an accurate picture, but is good enough to explain how the heat transfer happens in nuclear reactors using gas medium. And also, it is used in high temperature metallurgical processes like arc welding of metal and alloys, because these are inert. In electrical bulbs, argon is used to provide inert atmosphere. In earlier incandescent bulbs, argon was used because otherwise carbon filament will be oxidized immediately